Okay, the second concept of the equations in fluid mechanics is called momentum equation. Momentum equation, in the simplest definition, momentum is defined as the multiplications of the mass by velocity. Okay, a mass of the body times the velocity of the body. So to just prove this kind of like a concept, let's just review some of the laws of Newton. Okay, the first law is that we said the body will remain in the same condition of rest or of motion with uniform velocity in a straight line until acted on by an external force. That's the first law of Newton. The second law of Newton saying that the rate of change of momentum of a body is equal to the force acting upon it and takes place in the line of action of the force. Okay, let's just focus on this one. So the changes of the momentum of the body is equal to the force acting on that. To the force acting on that, if the body mass is m, the force acting on that, we just equate that one. The force acting on that, imagine it is denoted by F, and the change of the momentum, we can say the momentum is defined by m and velocity, mv. So the changes of the momentum, v2 is like to represent the final velocity, mv2 minus mv1. So these two means the change of the momentum over the time. Okay, so it's equal to the force. So that's like based on the second law of Newton. So if you can factor m from this equation, it will be outside the bracket. So m inside the bracket, v2 minus v1, the difference of the velocity, the final and initial velocity, and outside the bracket divided by t, the time that the moment applies or the time that the force applies. As you can know, you can see here, so the difference of the velocity over the time, we have like another term or parameters, which is called acceleration, so or variable, sorry. So the variable of the acceleration of the body is the difference of the velocity over the time. So we can just simplify and write this one as F is equal to ma, which is the second moment of the second law of Newton, and you're all familiar with this formula. So let's look at this. Is not a new one. This is something that we knew from the physics in the past. Okay, but the moments what we have in fluid mechanics, we need to just work on that a little bit more. Based on the third law of Newton, we can just, there's a fact, for every action, there is an equal and opposite reaction. You know, this is like the third law. Okay, let's look at this one. So let's look at trying to just work on the second moment law of Newton. So we have this formula, F is equal to m times, inside the bracket, v2 minus v1, all together divided by t, the time. So if you just consider m over t as like a one term, we can write m divided by t, we can write in different way. So we can write, we learned like the concept of the flow discharge. Discharge is denoted by Q, and we know the density. Density, we can just write m over t is equal to rho Q. Okay, so they are exactly the same. So let's just do some dimensional analysis to see how it works. Okay, so the m divided by t, the units are kilograms by time, or kilograms divided by s, or second. Okay, kilogram over second. How about like the rho Q? Rho is a density, is kilograms over cubic meters, sorry. And times the Q is the discharge, is the cubic meter, is the flow discharge, is the volume divided by the time, cubic meters by second. Okay, so if you have here in this kind of like multiplications, fraction to fractions, cubic meter from the bottom of the ratio can be canceled out with the top cubic meters here, and what is left is kilogram per second. So we have like a kilogram per second in here. Okay, so it's completely makes sense that we can just replace m over t by rho Q. So if you can substitute this kind of like a term in this equation, we will have this equation. F is equal to rho Q times V2 minus V1. Or you can simplify Q as substituting by A1 V1, or you can say A2 V2, because all the same, we're assuming that the flow discharge are fixed or constant. So we can write F rho A1 V1 or rho A2 V2 times V2 minus V1. Okay, so this is called momentum equation in hydraulic systems. So let's look at the more concepts on that. Some of the application of this concept. Before going to some of the applications, I'm just going to give you some example of the bending pipe. Imagine in some cases, once you just analyzing or you designing the pipeline system, the pipe has to bend because of the for example, change the direction. So for that reason, it's fine. However, there's a problem with that. If you have a piping system, the water has got the momentum or the push this kind of a pipe. Once it has to change the direction, it push this side of the pipe and push to the external side. So this is the momentum because of the change of the direction. As a very simple example of this one, I can give you, once you just have a hose, hose like a plastic pipe. And once you just, if it's the empty is fine, but once you just turn on the tap and the flow running through the hose, you can see the hose is kicking. And if you just increase or turn up the volume of the flow, you can see that kicking is more stronger. And try, you can see the hose is just changing. And that changing is because of the momentum. And because the flow try to just put a pressure on the external sides. So for plastic pipes, it completely makes sense. I mean, for example, let's say for the hose, that is a very flexible plastic. However, once you're just looking at a very solid or firm the pipelines, like the metallic or concrete pipelines, this kind of the force cannot, this kicking has to be supported by using any kind of external support. This kind of support could be the metallic or steel or concrete structures to support this one, to make sure that the pipe is not going to move. Because if you have the concrete pipelines, if this kicking can just cause the damage, or even could cause the burst of this kind of the pipeline. So we have to make sure to stop this kind of the kicking and the movement on the pressure. So this kind of a force is shown by FR is perpendicular to exactly to the bend direction. Can you see this bend is exactly in right angle to this one? And you can see here. So for the analysis of this one, imagine the velocity, the input velocity is the V1 and the exit velocity is the V2. We can extract some control or some volumes of the water inside the pipe. We can call it control volume. Control volume is denoted by this dashed line here. And we can denote our all external forces applied to that. If we can just take this kind of this shape of the volume of the water from this kind of the pipe, the external forces that we have, if one force applies behind this kind of the control volume, based on the pressure that we have and the cross-sectional area P1 and cross-sectional area A1, F or F1 can be written as P1 times A1. Remember, force is pressure times the area, or we can substitute pressure is the force divided by the area. If you can substitute that one, force is equal to P1 times A1. So this is the force, okay, or the pressure distribution times the area. Remember from the first chapter. And also the external or the outlet here. So this is the outlet, or this is the inlet of the pipe is the outlet of the pipe. The force applies to this section is the P2. If the pressure is a P2 and the cross-sectional A2, the forces F2 is equal to P2 times A2. Okay, you get denoted here. And the next one is the external forces applies here. But all of these are supposed to be the same as the external forces FR, resultant forces. Resultant forces can be divided into two components of the FRX, horizontal components and vertical components, FRY, okay? So that's something we're just gonna need to write it here. And we should be able to calculate FR, and that's the task that we need to do in here. So let's just do more calculations to just make sure how we can calculate this one. So imagine the problem is shown in here, and we have a control volume here around the pipe bend, and we can write all the external forces here by writing equations for both directions. Directions X and Y, we can easily write the equations and the equilibrium for both directions. Let's look at the algebraic forces. On the left hand side, we're just gonna write the algebraic forces, the sum of the Fx, or in each direction, and X direction is equal to the momentum on the right hand side, or the change of the momentum times rho q. So we can just write the rho q v2x, so the velocity at the x direction, or the components at the x direction, minus v1x, so the components of the v1 at x direction. And the same, you can write it, the algebraic forces at y direction. Algebraic forces means that whatever, if you're just going to assume this xy direction here, so whatever on the right hand side, forces applied to the right hand side is just assumed as a positive, or the upside for the y direction is a positive, or the downside is a negative for y direction, and the left hand side will be negative for the x direction. Okay, for example, here you can see this force is to the right hand side, exactly has got the one component of the x, there is no component to the y. Here FR has got a component in the Fx in the negative, can you see negative, and FRY is a positive for y. And here you can see, you can imagine that F2, or the P2A2, has got two components of the x and y direction, both negatives. Okay, so let's look at this, how we can just write here in both directions. So in x direction, we can easily write P1A1, okay, in x direction, 100% in x direction, but P2A2 is a negative. But to just get the components in x direction, we have to use the geometry and the trigonometry, cosine theta. So what is the theta? The theta is the angle of the bend here, the theta. You can just the projected value on the x direction is is calculated by hypotenuse. This is imagine this hypotenuse, and this is adjacent to the theta. Theta can be here as well. So P2A2 cosine theta. Okay, so that for that direction, this is with the minus sign. And here FRX, which is in the negative direction, can you see the positive R on the right on the top? So the x direction, FRX is in this direction, reverse direction. So if we assign negative on the left hand side, on the right hand side, rho q, okay, V2, the x direction, V2, which is this one, is got two components of the x and y, exactly the same as the force. So V2, the components on the x direction, you need to just multiply that one, V2 times cosine theta minus V1. V1 is the x direction. You can write the same for the y direction. For the y direction, we have a one positive FRY, and for the F2 or P2A2, it's a downside components on the y direction. So you say the minus P2A2 sine theta, okay, is equal to rho q V2. So rho q, and for the velocity components, we only have V2 components, V2 here. V2 here, which is actually on the upside. So it's not the downside. So the V2 here, so just look at here, the V2 is always positive, by the way. And the V1 in here is always negative. It's not the algebraic things, algebraic the direction applies only to forces, not to the velocities. Just bear in mind, this is very important. Can you see all the time? You need to just calculate the components of the x or y direction, but the sign, we are not following the algebraic sign for the velocities. Velocity is always velocity 2 components, is taken away, is plus minus v1 components of that direction. Okay, is always minus if you have any. For the y direction, we only have v2 components of y direction. If it is like the theta is here, the v2 in the vertical direction is calculated as a v2 times sine theta based on the trigonometry, is like a hypotenuse, and the vertical side is the opposite of the theta. Okay, so it's calculated as the hypotenuse times sine theta. That's the point. v2 sine times sine theta. And for the v1, we don't have any components in the y direction. So, okay, you can just write it here. So by solving these two equations, we can easily calculate frx and fry. And you know better from the first chapter, the resultant force can be equal to the square root of the sum of the squared elements of the components x and y direction. Okay, so a square root of frx squared plus fry squared. And theta, and the phi or the phi direction can be calculated. This is the angle of the phi. This is not the angle of the bend. The angle of the bend is the theta, but the phi or phi is the angle of the resultant force. It is calculated as the arctangent of the fry, the opposite one, divided by the frx. So it's an angle to the horizontal direction. Okay, so for the next example, we just look at the bending of the pipe while we have like this is like a vertical plane. So imagine this is the horizontal plane. The horizontal plane, we only have input force, output force, and the external force. However, for the vertical plane, we have another like the force applied, which is the W. W is the weight of the body based on the gravity acceleration. This applies to that. And once you're just going to push the water upside, the weight of the water is downside, is like the resistance. So we have to take that force into account while you're just going to ride in the this direction, vertical direction. Let's say we can show this one in the x and z direction. So because it's like a vertical, we can show it in the z direction. The only difference with the y direction that we just discussed last previous slide is that in here, for the components of the z direction, the only difference is that the additional the elements of the weight is added here, but with a negative sign. Okay, so if you compare these two formula, either z direction here or the y direction here, the only elements added here is the z or the w. So frz, this is a positive one, minus w, because w is like the negative downsides, minus P2A2 in y in z direction. Okay, let's say this is z direction. P2A2 is a force in this direction times the sine theta. So that's all the difference that we have. Okay, so next we just look at the example, how we can just resolve or how can we just use this kind of like equations or these kind of like relationships to just solve some examples.